Hi, this is John Whitaker for the Mathematical Analysis 1 class, and this is our 23rd video lecture. And we left off last time dealing with Cauchy sequences, and we were in the midst of a theorem that had 3 parts, 2 of which we had proven. I'd like to start off by stating and proving that third part of the theorem. So the third part of the theorem, part C, said in RK, every Cauchy sequence converges. Okay. So we would like to prove this, and here is the proof. We're going to let x sub n bar be a Cauchy sequence in R sub k. Then, as a construction that we had before, we're going to let E sub n be equal to x bar sub n, x bar sub n plus 1, and so forth forever. Okay. Then, as proven previously, in the midst of a fact, what we have is the diameter of the E sub n, well, the limit of the diameter equals to 0. So the limit as n goes to infinity, this diameter equals to 0. So this is a sequence of numbers, and so what we say then, so there exists I'll say a capital N sub 1 that is an element of the natural numbers, such that for all big N bigger than that big N sub 1, the absolute value of the diameter of E sub n minus 0 will be less than whatever we choose. Whatever we choose, the N sub 1 will depend on that. And we'll choose 1. And, okay. So, in particular, the diameter of E sub n sub 1, that will be less than 1. What that tells us, then, thus, the distance between x sub n and x sub n sub 1 will be less than 1 for all big N bigger than or equal to n sub 1. Now, what we're going to do is observe, note, that the range, so the output values of the sequence x sub n, well, that's equal to E sub n sub 1, so that's all the terms from the n sub 1 term beyond, union with x sub 1, x sub 2, all the way up to x sub n minus 1. And what we're going to do is we're going to let m equal to the maximum of the distances between the x sub 1s and x sub n. The maximum of these distances. And here, the next distance we're going to consider is x sub 2. the distance between x sub 2 and x sub n. And here I should say n sub 1, I think. Yes. And continuing on all the way up to the distance between x sub n sub 1 minus 1 and x sub n. Okay? And one more thing, and 1. Okay? Then what we get, this is going to force the distance between x sub n and x sub big N sub 1, that will be less than m plus 1, if you will, for all n element of j. So all the terms of the sequence, their distance from this particular term will be less than this particular number. Less than or equal to less than. That gives us that the x sub n's are bounded. And that's what I'm going to write next. So, x sub n's is a bounded sequence in our case. This implies that the closure of the set of the x sub n bars, closure of that range, is bounded. And this can be thought of this is true because if P bar is a limit point of this sequence, then that means there exists a subsequence remember, if you're a limit point of a set, there's a sequence within that set that converges to it. And so here, since our set is the output values of sequences, we're saying there's a subsequence of x sub n, say x sub n sub I running from 1 to infinity, such that, I got just enough room here, the x sub n sub i's converge to P. Okay. So, what that says is there exists a K that's a natural number such that for all I bigger than or equal to this K, the distance between x sub n sub I and P will be less than whatever number I'd like, and let's say that's M, any positive number I like, it's M. In particular, we could say that the distance between x sub n sub k and P will be less than M. Then, if you take a look at the distance between P and x sub n sub 1, well, that's going to be less than or equal to the distance between x sub n sub k and x sub n sub 1 plus the distance between x sub n sub k and P. This is true by the properties of the metric. Okay. And this guy right here, it's, the x sub n sub k, its distance from this particular term of the sequence. Remember, we showed you that all the terms of the sequence, their distance from that one is going to be less than m plus 1. Okay? Plus, here, this is going to be less than m, so we have m. This is strictly less than, which is equal to 2m plus 1. So, all the terms in the closure, their distance from x sub n sub 1 will be less than 2m plus 1. Let me write that down. So for all points in the closure of the sequence x sub n bar, these points, they are either, well, they're either terms of the sequence or limit points of the sequence. Either terms of the sequence or limit points like our p-bar. Of the sequence. In either case, the distance between that point, whatever they are, and x sub n sub 1, that's going to be less than 2m plus 1. And that's for all x n, that's for n, the closure. Of this sequence. Okay. So we know that the closure of this sequence is closed, and now we know it's bounded. Okay. So by a previous theorem, we're in RK. By a previous theorem about RK, since this x of the closure Since the closure of the sequence is closed and bounded, then the closure is compact. Closure of the X of n is compact. So it's compact. Probably be an R, okay? So what we do is, if we restrict, so we restrict the metric on RK to the closure of the X of n then X of n bar must converge to some point in the closure of X of n bar which is a subset of R sub k. Thus, that means that the X of n bar converges in RK. And that is the proof. Okay, the next thing we'll do is the definition. He said it says that a metric space in which every Cauchy sequence converges is said to be complete. So example, RK is complete. We just showed that. 2. All compact metric spaces are complete. And 3, we look at the set 0 to 2. It doesn't include 0, but it does include 2. And we have only the metric d of xy equal to the absolute value of x minus y. then this space is not complete. So it is not a complete space. And the reason it's not complete is as the sequence 1 over n is Cauchy, and 0 to 2 are space measures with that metric, but does not converge in 0 to 2. And the reason is that it's supposed to, in the real number line, converge to 0, but 0 is part of this metric space. Okay, here's a comment. We have proven that every convergent sequence is bounded in a metric space but it's not the case that every bounded sequence is convergent. Down. However, not every bounded sequence is convergent. Let me show you an example. For instance, -1 to the n, which equals to -1, 1, -1, forever, is bounded it's bounded because the distance of all these points from 0 will be less than 2, if you will. It's bounded, but -1 to the n does not converge. Now, however, for what are called monotonic sequences, boundedness implies convergence. So we are going to study monotone sequences. What are they? Well, that's what's next. So here's the definition. We're going to be working in real numbers here. We're going to say a sequence S sub n of real numbers is said to be, so we get two definitions, monotonically increasing if S sub n is less than or equal to S sub n plus 1, and that's true for all n greater than or equal to, or all n element of j, I should say. And part B, monotonically decreasing if S sub n is greater than or equal to S sub n plus 1, and that's true for all n element of j. Okay, so in this setting, hey look, your monotonically increasing is if you never get smaller as you go to the right, go further along in the sequences. And here you're monotonically decreasing if you never get bigger as you go to the right in the sequence. We've got an all-encompassing definition upcoming in terms of these words. Definition. A monotonic sequence is a sequence that is either monotonically increasing or monotonically decreasing. Okay. So, you know, we said that if you're bounded, you may or may not converge. You may not converge, okay? But I said, well, look, for boundedness for monotonic sequences, it's going to apply convergence. We're going to get to that in just a second. But I should say, we're talking about monotonic sequences in the real numbers. That's what the setting that we're living in right now. Well, let's first look at some examples of monotonic sequences. So if we let x sub n equal to 1 over n, then is a monotonic sequence. In particular, it's monotonically decreasing. Let's look at that. So as a proof, note, so here's what we start off with. Just look at the natural numbers. We know that n is less than or equal to n plus 1. Previous natural number is less than the next one, less than or equal to. Okay, that means if we divide both sides by n, we have 1. Let me say this is true for all n element of j. So, for all n element of j, we divide everything by n. We have 1 is less than or equal to n plus 1 over n. Now if I divide everything by n plus 1, we have 1 over n plus 1 is less than or equal to 1 over n. But that's the s of n plus 1 term. So for all n element j, we have s of n plus 1 is going to be less than or equal to s of n. And that means 1 over n is monotonically decreasing. Okay. As another example, the sequence is 3 minus 1 over n is monotonically increasing. We won't prove that. And it's much like the proof we just gave. So here's the proof. Well, note, as we said before, n is less than or equal to n plus 1 for all n elements j. So this means that we divide by n times n plus 1, we're going to get 1 over n plus 1 is less than or equal to 1 over n for all n elements j. So if we multiply everything by minus 1, we get that minus 1 over n plus 1 is greater than or equal to minus 1 over n for all n elements j. And now if we add 3 to both sides, we'll have 3 minus 1 over n plus 1 is going to be greater than or equal to 3 minus 1 over n. And that's true for all n elements j. But this is s of n plus 1 is bigger than or equal to s of n. That's what this is for all n elements j. So the next term is bigger than the previous one. So the s of n, which was 3 minus 1 over n, is, all right here, monotonically increasing. Okay, good. Lastly, let's look at an example that's not monotonic. Okay, a final example, minus 1 to the n is not monotonic. And here's the reason. You know, this minus 1 to the n equals to minus 1, 1, minus 1, 1, and so forth. And so this is x of 1, this is x of 2, this is x of 3, this is x of 4. So here, note that x of 1 is less than or equal to x of 2. So maybe it's increasing. But x of 2, well, I should say strictly less than. Here, x of 2 is greater than x of 3. So it can't be increasing because here we have a problem. And it can't be decreasing because here we have the opposite. Okay. Well, here's the theorem. it's sometimes called the monotone convergence theorem. Here's what it says. It says, suppose S of n is monotonic in R. Then S of n converges if and only if it is bounded. Converges if and only if S of n is bounded. Let's look at the proof. Okay. So let S of n be a monotonic sequence in R okay. So this proves an if and only if proof. So let's go in this direction. So here we're going to suppose. This is the more difficult direction. Suppose S of n is bounded. We want to show it converges. Okay. All right, we're going to consider two cases in our setup because we know that S of n is monotonic. And so it's either monotonically increasing or monotonically decreasing. So here's case one. Suppose S of n is monotonically increasing. Okay, that's our case one. Okay, then first thing we'll say, what does that mean? It means that S of n is less than or equal to S of n plus 1 for all n elements J. That's what we know. Now let's let E be the range of S of n. We're talking about the output vice versa, the terms, the numbers that make up this sequence. Since S of n is bounded, there exists a P element of R and an M that's greater than 0 such that the distance between S of n and P will be less than M, and that's true for all n element J. That's where we are. That's the boundedness part. So, for all n element of j, here's what we have. The distance between s of n and 0 will be less than or equal to the distance between s of n and p plus the distance between p and 0. And we're thinking about the usual metric here. This will be less than m plus the absolute value of p. So when I said we're thinking about the usual metric, the distance between s of n and 0 can be represented by a difference within absolute values, and that's what I'll do next. So, for all n element of j, what we have is that s of n minus 0 inside absolute values will be less than m plus absolute value of p. So what that gives is that the absolute value of s of n is going to be less than m plus the absolute value of p. And that's true for all n element of j. So, here, rewriting this, we'll say for all n elements of j, we have, this says that m minus absolute value of p is going to be less than s of n, which is going to be less than m plus absolute value of p. And that says s of n, we think of it as a set, is bounded above all the terms are bounded by m plus the absolute value of p, I should say. Okay? And they're bounded below, but I'm not going to worry about that bounded below so much at this point. Okay, they're bounded below like this. So that means E, that the sup of E, which is the range values, exists. Call it S. And what we're going to do is show that the sequence S of n converges to S. S of n converges to S. That's what we're going to show. So remember, use the definition of convergence. We kind of have to know what it converges to. Use that epsilon definition. And so now we have a candidate for what it could converge to. So, how do we show convergence using definition? We let epsilon be greater than 0 be given. We need a k element of the, I guess I call it n element of the natural number j. Okay. Such that for all n bigger than or equal to this big N, S of n minus S will be less than epsilon. Okay, well, note, since the since S equals to the sup of E, then S minus epsilon is not an upper bound of E,
So that means there exists n element of natural numbers such that s minus epsilon will be less than s sub n, okay, which is less than s. Now, since S of n is increasing, then for all n bigger than this big N, we have S minus epsilon is less than S of n, but that's less than or equal to S sub little n, because the little n is bigger, so you're to the right of the sequence. And that's going to be less than S of epsilon, S, because that's the suit. And I can say it's less than or equal to, really, that's what it should be. I just said less than up there. Less than or equal to. But that's less than S plus epsilon. And so, what this says is that the absolute value, well, first of all, let me subtract S from, let me rewrite this. For all n bigger than or equal to big N, we have S minus epsilon is less than S of n, which is less than S plus epsilon. So we write it a little bit more concisely with the objects we want to be looking at. So for all n bigger than or equal to big N, this says, if I subtract S from both sides, minus epsilon is less than S of n minus S, which is less than epsilon. And that says, for all n bigger than or equal to big N, this is inequality we can translate using absolute values. And that says S of n minus S is less than epsilon. This is the distance between S of n and S. And so that shows that S of n converges to S. So that ends it for this case. Now case 2 is when we have S of n being monotonically decreasing. It's going to work very similarly. Decreasing. Then S of n plus 1 is going to be less, so it's decreasing. So decreasing. So the next one is going to be smaller than the previous one. Again, we're going to let E be the range. It's going to be very similar to what we did. Of S of n. We know E is bounded. Okay, and it's bounded both above and below, so we'll concentrate on the below part. So we know that the infimum exists. Let's give it a name. Let's call it S prime. Okay. And what we're going to do is we're going to show that the S of n is converged to S prime in this case. Now, we're going to okay, so we're going to let epsilon be greater than 0 be given. Okay. And here's what I'll say. Since S prime equals to the theorem of B, then if you add something to that, add a positive part to that, it's not going to be a lower bound. We're getting close to being done. And I've already written. Okay, then S plus, or S prime plus epsilon is not a lower bound of E. So there exists an N element of natural numbers such that S of N will be less than S plus epsilon, since the S of N's are decreasing. For all N bigger than or equal to this big N, we have that S of N will be less than S plus epsilon, but it's going to be bigger than or equal to S of N, little n, which will be less than epsilon, less than or equal to, not epsilon, but S. So, for all N bigger than or equal to big N, here we have S minus epsilon will be less than S of N will be less than S plus epsilon. So, for all N bigger than or equal to big N, we have here, this is going to be S of N minus S will be bigger than minus epsilon, get less than epsilon. So for all N bigger than or equal to big N, the absolute value of S of N minus S is less than epsilon. What that says so S of N converges to S. Okay. Look, what we've done is we've shown that if you're a monotone sequence and you're bounded, then you converge. The thing we have to show next, remember this is an only statement, it's really easy, is if you're convergent, monotone and convergent, then you're bounded. That's this direction. Okay, we're assuming it's convergent, and we've already assumed it's bounded. Okay, well, since S of N is convergent, we've already proved it. Okay, by previous theorem. That ends the proof of the monotone convergence theorem. That is enough for today. Thank you very much.